In this video, we're going to look at three different things. First, we're going to look at the fundamental counting principle, and then we're going to talk about permutations, and after that, combinations. Let's first take a look at an example of the fundamental counting principle. An example of looking at the fundamental counting principle is if we're, say, to visit a yogurt parfait place. And here's my options. I can choose one flavor, I can choose one fruit, and I can choose one nut. So from here, well, let's look at how many combinations we can possibly make. If I start with just plain Jane yogurt, and then I also go with peaches, and then I choose almonds, well, that is one choice, because I went from peaches to almonds. Okay, and then from there, well, I could also choose plain and peaches and peanuts. So there's plain, peaches, and peanuts. Or I could also choose plain peaches and, let's choose a different color here, plain peaches and walnuts. So plain peaches and walnuts. Okay, now another way that I could think of this, there's one set of three, so three. I could do plain, and then I could do strawberries. And then with the strawberries, I could also choose almonds, peanuts, and walnuts. So that would be a set of three. And then with the bananas, here, let's do yellow for bananas. I could choose plain and bananas, and with those bananas I could also choose almonds, peanuts, and walnuts. So that's another set of three. Okay, then with raspberries, well, I could have plain and raspberries and almonds, peanuts, and walnuts. So there's another set of three. And finally, my last selection choice is I could do plain with blueberries plus almonds and peanuts and walnuts, which is another set of three. Well, if I add all of these up, I end up with 15, which makes sense. And then if I was to, say, look at a different type of flavor, so let's say I choose vanilla, but I repeat my steps through peaches, strawberries, bananas, raspberries, and blueberries, that means I'm also going to have three different options for each one of these sets, which also equals 15. And if I'm to add everything up, well, there's a total of 30 combinations. But another way one can look at this, which is even easier, is I could just simply look at the number of options I have under flavors, which is 2, and then the number of fruits that I have, which is 5, and the total number of nuts choices, well, that's 3. And I can just say 2 times 5 times 3, which equals 30. And that's the total number of options I can have. Next up is permutations. Let's look at this problem where an art gallery has 9 paintings from an artist and will display 4 from left to right along a wall. In how many ways can the gallery select and display the 4 paintings? Well, let's think about it this way. Let's start off with, we have a total of 9 paintings. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and in this case, order is really important because we want to make sure that the artist has exactly what they want. In other words, it would be very different if we had the flowers over where the zebra is and the zebra over where the flowers are. So we want to have that order correct. Okay, first thing though, let's just look at our options. When I choose the first painting, I have 9 different paintings to choose from. In other words, I can look for, let's give ourselves a color here, I can look for 9 different paintings. After I've done that though, that means that 1 is up on the wall and I have 8 paintings more to look at. Okay, so now, and remember I'm only choosing a total of 4, next time I choose one, let's say that I'm going to go for, this one right here. Okay, so that one is now up in place, so let's call that the bull. And that means that I chose it from a total of 8 different paintings. Okay, now next up we need to get our third painting and we have a total of 7 to look at. So let's say I use this one. Alright, so now that chose from 1 in 7. Okay, and then lastly I've got one more to choose, and let's say I choose this one as my frog. So that's my 4th one. Well, of the total that I could choose from, 1, 2, 3, 4, 5, 6 is times 6. Okay? And this is just going to give me the total number of paintings that I could look for. So 9 times 8 times 7 times 6, 3,240 options. Wow, that got pretty big pretty fast. So the official way that we can look at permutations, it all boils down to an equation that looks like this. It says n and then a capital P and then a little lowercase r. N right here, this is the total number of options, so number of options. P stands for permutations, and R stands for the number I want. Okay, so if I was to describe this whole problem as NP of R, the number of options that I have total is 9 paintings. There's my P for permutation, and then R, the number that I want, is 4. Okay, now the way that we can write this is using a character called a factorial, and factorial means 9 times 8 times 7 times 6, but it also goes all the way down to 1. In other words, say 4 factorial, that's the same thing as, make that a big exclamation point, that's the same thing as 4 times 3 times 2 times 1. Okay, so in this case, the equation that we're going to use for any factorial is going to be n factorial divided by, and then in parentheses with a factorial outside, n minus r. Okay, so what that means is n, that's my number 9, so 9 factorial is going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. There's n factorial. And then n minus r, in this case, that's going to be up here, let's just do this little 9 minus 4. So 5 factorial. Divide this whole thing by 5 factorial. So 5 times 4 times 3 times 2 times 1. Okay, now the cool thing about this is there's a whole lot of math that we can take care of. We can start canceling things out that are on top of each other. Things that I want to cancel out, well, I want to cancel out that 5 and that 5, 4 and 4, 3 and 3, 2 and 2, 1 and 1. And so then ultimately what we're left with is 9 times 8 times 7 times 6, which is exactly what we did right here. That's an example of a permutation. Lastly, let's talk about combinations. With combinations, they're very similar to permutations, and the way that you can write those is with an n, and then instead of a c, we'll use, or a p, we'll use a c. So n, c, and then r. And n is the total number you have, so number you have, and r is the number you want. Now here's the difference. When we're working with combinations, order does not matter. Okay, let's write this in big blue letters. Order does not matter. And the way that I remember this is if I'm going to McDonald's, I'm going to order a combination number 2. And in a combination number 2, I could get a Big Mac, fries, and a Coke. I could get fries, a Coke, and a Big Mac. I could get a Coke and fries and a Big Mac. Oh, I think I already said that one. I can get whatever order I want, and either way, I still have my combination number 2. In other words, the order doesn't matter. Okay, so in this problem here, well, what we have is there are 12 different colored cubes in a bag. How many ways can Randall draw a set of 4 cubes from the bag? So let's start off the way we have in the past, and we're going to use factorials, in other words, exclamation points, to start off with. So in my first set of 12 that I pull from, well, I have 12 different possibilities. So there's 12. After that, I pull out another one. Well, that's going to give me, I have 11 choices to choose from. Now that I've pulled out 2, I have 10 cubes in the bag. Okay, so I'm going to choose from 10 of them. And now I've chosen 3, so that gets me down to 9 different choices that I can have in the bag. So my last selection is going to be 9. The trick with this, though, is let's say that I've pulled out a blue cube, and I've also pulled out a black cube, and then I've also pulled out a lime green cube, and I've pulled out a red cube. Well, I could rearrange these in a whole bunch of different orders. I could go blue, green, black, red. I could go red, black, green, blue, blah, 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 blah. And the only thing that's important is in Randall's hand, how many squares or cubes does he have? The answer is 4. So what we're going to have to do is we're going to have to divide this by a number that will lessen the number of repeats, because I only care how many squares or cubes are in his hand. So what I'm going to do is I'm going to do a division here, and well, I suppose now is a good time to look at the equation. The equation for n combination r is n factorial divided by n minus r factorial all times r factorial. Okay, so let's erase some of these here a little bit and give ourselves a little bit of room to write. Okay, n factorial, well, 12 times 11 times 9, well, times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So there's that n factorial. And then n minus r, well, if I was setting this n and cr, let's set that up so we have something to look at. N, cr, my n, that's the total number I have, which is 12, c, and then r is how many I want, which is 4. Okay, so on the top I did n, which gave me 12 all the way down to 1, and then for n minus r, well, that's going to be 12 minus 4, so that's 8 factorial. So there's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, that's one part. And then the last thing I got to remember is this r factorial. And r factorial, well, that's just 4 times 3 times 2 times 1. Now the cool thing is that all of these pieces, 8 and 8, those cancel out. 7 and 7, 6 and 6, 5 and 5, and then, well, all of those just cancel out. So what I'm left with is 12 times 11 times 10 times 9 divided by 4 times 3 times 2 times 1. 12 times 11 times 10 times 9, that ends up being 11,880. So that's a pretty big number, 11,880. And then 4 times 3 times 2 times 1, well, that is 24. Okay? And when I divide those two numbers out, I get 495 options. So it's a lot bigger than one would have thought, but it's a whole heck of a lot smaller than permutations, and permutations was if order mattered.